you where we are going to um, discuss about this mechanical design interview questions, but with perspective of how do we select material for a given design. Again, we will be going through this interview sort of scenario with Mr. Samuel, and let's just dive into it. So, as a recap of what previously we discussed in part one was the problem statement was very straightforward, where we have a doorknob. A new doorknob design has been released, but it is failing at various installation bays. And when it was further inquired that why this particular design is failing, it came to the attention that the load bearing capacity of this particular doorknob is not enough. And when it is being handled with people are hanging their bags and like children are climbing onto it, and this doorknob is failing. So having this information, we were asked to improve the design. And uh, earlier we just converted this whole scenario into free body diagram, as can be seen. We replaced the grocery bag weight with force F2, self weight of the doorknob with force F1, and the reaction force by force FR. We consider for the simplicity of the discussion as it's a knob with length L, and the cantilever load is happening with the shape of this beam being uh, a rectangular one, which has a height of h and breadth of b. So yeah, this is just a recap. Uh, so I hope now we understand where we were. Previously, when we tried to solve this issue, we tried to minimize this deflection. And the way we minimize this deflection was by looking into decreasing the length, because it's a cubic relation, and how to increase the moment of inertia and thereby decreasing this minimizes deflection. But today it's more about how, how do we reduce the deflection without playing with any geometrical parameters. And as can be seen, right, like the other way is where we can play with this E, that's modulus of elasticity. And since it's in denominator, so if I have to decrease the deflection, I have to increase this modulus of elasticity, uh, which is very straightforward. So let's look like how do we select the material, which is, I think, one way I look into it, but you can have your own like database where you can look into it. So the plots which are shown here, they are called Ashby's plot. And there is a software, GrantaDesign. As a student, like you might find a student version which is free. Uh, this charts, anyways, you can find it on like Google Images. It's by GrantaDesign. It's called Ashby plots. This particular one is like the y-axis is listed as Young's modulus and density. You can plot it where various different axes, like if you are calculating factor of safety, you can like look into stress, strength of yielding strength and ultimate tensile strength and plot it against that. Um, but for simplicity of this discussion, we will be focusing on like how do we select the material. And based on the previous equation, our objective right now is to increase modulus of elasticity, right? So just follow this line, move it up, 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 and then you can like find what are the materials which have high Young's modulus. As it's very evident, like you can see, most of the metals have high Young's modulus, so do ceramics. And then there are certain composites which do have high Young's modulus. Um, since the density is plotted here, you can also see that these are highly dense material also. On the lower half are like natural materials like wood and foams, polymers, and elastomers. As we know, they have like lower Young's modulus, and also for most of them have like lower densities. But since our objective was to increase E no matter what, So this is the area which we can like narrow down to, that if I have to select a knob, I will try to make it with the metal. It could be copper, it could be lead, it could be aluminum, it could be stainless steel. This metal has a big range. It also highlights that we can make it out of like ceramics, diamond steel, uh, alumina, that's Al2O3, silicon nitride, silicon carbide. Although based on our problem statement, it is true, we can do it. But I would highly suggest not to do it, because first, like, diamond is super expensive. You don't want to have a doorknob made up out of diamond. Other materials like aluminum and silicon nitride, this are sturdy. It's just that they have a tendency to break because they are brittle and because they are ceramic. So given a choice, I would go with somewhere in this metals side. Uh, I will go further in details, like how do we narrow down it, because this was like a very simple question which is normally asked in interview question, like how do you select materials. But actually how it happens, like, or how I do it is, uh, yeah, what's the criteria for material selection? So it's straightforward in a way that I first identify what's the function, like what is this component doing for the overall assembly, which helps to narrow down, like um, whatever I select this material, whether it is able to deliver the basic functions. Then what's the objective I'm trying to solve? Like in the previous case we discussed, we were trying to increase the modulus of elasticity, but normally it's like coupled with some other factors as well. I can show you one example in coming slides. And then, like, are there any constraints, which is very specific when we go into any industry, that normally it's not just like the perfect material, but there are like other constraints associated with it, which you might find like which is meeting your objective, which is meeting your functions, but there are constraints where you cannot use any of them. So I will just give you a brief overview about how, like, an example sort of. So if you look into the doorknob question, right? What is the function of doorknob? What I can think of is like it's a doorknob, so it has to be like flexible enough, like it will open and close, and people are going to hang on to it. That's why I told, right? Let's not select ceramics. And second is doorknob. Like one of the things people might ignore nowadays, but it's doorknob is a handheld device. So many people touch it, and with now with COVID happening and all, right, people are more skeptical about bacteria and viruses spreading from one surface or contact on another. So with if you look into like popular doorknobs, brass, like, okay, brass is one of the material which is being used. It's so one of the characteristic of it is because it's like a self-cleansing, because it has a copper in it. So it does help. So even if we were just trying to maximize or minimize one of our objective, but functionality is important, because what if like it is a door handle for like a hotel or like a hospital or something like that, right? Um, so just another example, like we in those kind of scenarios, it's always better to look for are we meeting with that functional criteria? Are we like coating this doorknobs or something with the coating which is very hazardous to our health? So functions are important. Second is objecting. Second is to define the objective. So let's define. Earlier we were just maximizing our stiffness of this doorknob, but usually it's coupled. So in this case, I've said like let's minimize the weight while maximizing the stiffness. And you can find it any textbooks. Normally, it's very easy to derive those kind of functions. You just simplify it to the lowest possible level. Um, so here, like the material index, I have defined it like if you just simplify all this equation for a bending stiffness which you encounter due to the bending, it will come down to this where e to the raise, it's like modulus of elasticity raised to the power half, and this P is considered to be rho, that's density. So what it implies is like my objective is to maximize this material index, And if I maximize this particle function, it will give me a material which will have a good enough stiffness with a very low weight. So now let's look into the Ashby's plot. This kind of slopes, we previously looked into Young's same chart, but in Ashby's plot, it's a software and you can like pretty much define the slopes. And in our case right now, our function objective is slightly different than what it was previously. Now, for this material index defined for this bending case, uh, our objective is to maximize this particular function. And since now we want to even reduce the weight, so if I follow this particular slope, I can like move it upwards, but like moving it this direction won't give me any material because there is no material here. But if I move down, I can find like what are the materials which fall under this line. So I can follow this line. And if you see right now, since our objective changed from elasticity, just from elasticity, now we are concerned more about weight and mass. So some other materials seems more like close to metal now, like this foams and like particularly this natural materials, right? Like wood and all, which if I make this slope down, this slope will hit this particular section before metals because metals are highly dense. Um, but it's depend upon what you are trying to maximize and minimize. The other two, I mean, the other two slopes which are highlighted over here is one is if you are trying to solve the same problem, but instead of having a beam, you are trying to solve it for a sheet. And So the key takeaway from this is these are the slopes which you can like just plot in this GrantaDesign. It's a free software, and you can find and define which material you want based on your objective. The constraints. So this one is like when you go and when you actually design, these are like some of the issues which you have to first make sure that you solve them properly before even like looking into any of the material. So our constraint is we need to have a good enough bending stiffness because that's the problem which we were given. Second, it's we have to ask the supply team and marketing team and the people who are associated with it, like what is the margin which they are going to sell and how much is the budget in terms of like we cannot select, like as I told you, right? We cannot select diamonds because we can select diamonds, but it's just that are we ready to pay that amount of cost? Are our buyers ready to pay that amount of cost? And then manufacturability. So as a general rule, like you have to look into what are the manufacturing processes associated with it, whether it's a machinable part or whether you can make it by molding or casting. So like machining usually is expensive, and like if you have two materials like stainless steel and aluminum, stainless steel strong. It has high modulus of elasticity, right? But it is so stiff that it is very hard to machine compared to aluminum. So the cost associated with it and the lead time, everything increases when you have to just select between stainless steel and aluminum. And logistics, which is important because if like suppose you are doing an R&D project and you figured out exotic material, say like composites, fiber reinforced composite, which has a particular stiffness high in like a particular plane. But what if it is only made in Germany or some other place? You cannot just wait for like a month or 2 months to get like your prototype part at a higher cost. You have to make sure that the problem which you are trying to solve is logistically possible. It can be, it is scalable as well. So these are like some of the constraints which I found for doorknob problems which you can discuss with your interviewer, but every problem has its own constraints. So usually list down all three functions, objective and constraint, and then from there start narrowing down which material you want, and then use the Granta plot as I mentioned. As the last part, uh, we are going to go through geometric dimensioning and tolerancing, which is very important. The stack up tolerance and what kind of GD&T or what kind of tolerances which we can give. As a design engineer, it is one of the must thing to know, and normally it is being asked, like some sort of questions is being asked during the interview. So I sort of will find an example and will share in part 3. Until then, bye.